In this video, we're going to talk about multiplying and dividing radical expressions. Let's start with multiplying. As a review, we said that if n is the index and the nth root of a and the nth root of b are real numbers, then instead of multiplying these things separately, what we can do is write these under one radical and take the nth root of a times b. All right, this is what we're going to continuously come to in this section where we multiply and divide. However, now that we know how to simplify rational expressions, we're going to have some that aren't going to be a times b, probably won't be a perfect nth power. Let's look at some examples. In part A, we have 6 times the square root of 12 times 5 times the square root of 15. What we're going to do here is we're going to multiply the numbers that are on the outside. We have a 6 on the outside and a 5 on the outside. We're going to multiply those the same way we normally would, right? So 6 times 5 is 30. And then we're going to multiply 12 times 5 under the same radical since they're both square roots. Now, 12 times 5 is 12 times 15 is 180. And so this is going to be the same thing as saying 30 times the square root of 180. Right? Now, we've done the multiplication. We have one radical, but we're not done here because 180 is not a perfect square, but we have a perfect square that is a factor of 180. Just for purposes of making this a little easier, I'm going to list a couple of perfect squares. For instance, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, so on and so forth. All right. And basically what I want to do is, I know that 180 is not a perfect square, but I want to see which number or what's the largest perfect square that goes evenly into 180. And if you look at this list, there's a couple of these that goes evenly into 180. For instance, 9 goes evenly into 180, all right? 9 isn't the only one that goes evenly. 36 also does, all right? And if you think about it, I know I skipped 4, but 4 also goes evenly. I want the largest perfect square, and the largest perfect square is 36. 36 times 5 will give you 180, so I'm going to write this as the square root of 36 times 5. Of course, a perfect square never belongs under a radical. We can take the square root of that. The square root of 36 is 6. So I'm going to have a 30 times 6 times the square root of 5. Now, 30 times 6 is 180. And so in order for me to simplify this completely, I get 180 times the square root of 5. And that is my final answer in complete simplified form. All right. Let's go to part B. We have the cube root of x to the 4th y squared z times the cube root of x to the 8th y z to the 4th. Again, my radicals are the same. We have cube roots. So instead of writing these separately, I'm going to write it under one radical. It's going to be x to the 4th y squared times z, and I'm multiplying that by x to the 8th y z to the 4th. Now, of course, order doesn't matter when we're under the radical, so I'm actually going to multiply x to the 4th by x to the 8th. I'm going to multiply y squared times y, and I'm going to multiply z times z to the 4th, all right? So this isn't combining like terms, it's multiplying, and when your bases are the same, you add your exponents. So I'm going to have the cube root of x to the 12th, that 4 here, and that 8, y to the 3rd, that's a 1 exponent here, and then z to the 5th, because that's a z to the 1st power times z to the 4th power. Now I'm at a point where I've done my multiplication, I've got one radical, but I've got to make sure that my answer is simplified. All right, and so what we said before was we can separate these so that we won't get too confused when we do this multiplication. And the only reason why we can separate this is because it is multiplication under each of these radicals. Now, if you recall, in order to simplify, when we have powers of a variable, we look at the multiples of our index. For instance, our index is 3. The multiples of 3 are 3, 6, 9, 12, 15, so on and so forth. All right. And if we see those numbers, these exponents on this list of multiples, then it is a perfect cube. But if we don't, then what we're going to have to do is we're going to have to rewrite as a factor as two factors where one is the largest multiple of 3 that's less than the exponent. If you notice, 12, that's a perfect cube. That'll give us a perfect cube, and this 3 will give us a perfect cube. But the 5, on the other hand, will not allow us to do that. So I'm going to go ahead and rewrite that cube root of z to the 5th so equal sign there. So these are perfect cubes. I don't have to rewrite them, but z to the 5th, well, the largest multiple of 3 that's less than 5 is 3. I can write it as z to the 3rd power times z squared. Make sure I keep all that under my radical. Now, all of my perfect stuff, I'm going to take the cube root of, right? So remember, when we take the cube root, we divide the exponent by 3, right? So that's giving me x to the 4th. 3 divided by 3 is 1 times y, and 3 divided by 3 is 1 again times z. And this z squared is going to be left under my radical. So that would be the cube root of z squared. And this is my simplified solution. Not only can we multiply kind of like we multiply monomials, but we can multiply kind of like we have a binomial where we use the distributive property. So in this example C here, I have 8 square roots of 6 times the quantity 5 square root of 2 minus 9 square root of 3. I'm going to have to use my distributive property. Distribute here and distribute here. I'm going to write this out because we're going to actually have to do some stuff to simplify. When I distribute it to the first term, I get that. When I distribute it to the second term, I get this here. Okay, well, I'm going to multiply my 8 and my 5. That'll give me 40. And I can, since those are both square roots, I can write it as the square root of 12. 8 times 9 is 72. 6 times 3 is 18. All right, and so now, since I've done my distributing, I'm actually going to see if I can simplify any. Well, we have perfect squares. The largest perfect square that's a factor of 12 is 4, so I can write 12 as 4 times 3. The largest perfect square that's a factor of 18 is 9. I can write 18 as 9 times 2. Of course, the perfect squares, we can take the square root of them. Well, again, they don't belong under the radical. We can take the square root. And so I'm going to have 40. Square root of 4 is 2. So 40 times 2. Square root of 3 stays under that radical. Square root of 9 is 3. Square root of 2 stays under that radical. 40 times 2 is 80. So I get 80 square roots of 3. 72 times 3 is 216. So I get 216 times the square root of 2. Notice I can't simplify any further. This is my final answer. Those are not like radicals. The last example we're going to look at when it comes to multiplication, just as we see it here, is 8 square roots of 5 minus 7, that quantity squared. All right, always remember when you have a quantity squared, all right, I'm going to need some extra space here. What we have to do is we have to multiply it by itself. So don't try to square because that's a subtraction in the inside. You have to multiply it by itself. So that sets up that repeated distributive property, or what we call the FOIL method. So I'm going to FOIL this out. 8 square root of 5 times 8 square root of 5. Distribute to that. Minus 7 times 8 square roots of 5. Here, minus another 7 times 8 square roots of 5. And a negative 7 times a negative 7 is a positive 49. All right, of course, we're going to want to simplify. I get 8 times 8, which is 64. Square root of 5 times square root of 5 is square root of 25. Minus, well, 7 times 8 is 56, and I still have that square root of 5. Same thing happens here. So I get minus 56 square roots of 5 plus 49. Of course, we can simplify that even further. 25, if I take the square root of that, I get 5. All right, so that's going to be 60 times 5. These two are like terms, so if I combine those, negative 56 plus the negative 56 is a negative 112 square roots of 5 plus 49. All right, so we get 320 when we multiply the 64 times the 5 minus 112 square roots of 5 plus 49. And if we combine the 320 and the 49, we'll get 369 minus 112 square roots of 5. and this will be considered our final answer. Okay, so that's multiplying. We're going to look at one other type of multiplication by something special called a conjugate. So multiplying conjugates. And two things are conjugates if they can be written in this form right here. Two things are conjugates if they can be written in this form right here. I have x plus y times x minus y. So for instance, I may have something like 2 plus square root of 3 and a 2 minus square root of 3. Those two things are called conjugates. Note, you have the same things in your first slots, same things in your second slots. One separated by a plus, one separated by a subtraction. That's how we create conjugates. And I'm going to erase this because there's a nice property when we multiply conjugates. Of course, this looks like it sets up a FOIL method, which we will use here. So I'm going to FOIL this out. X squared minus x times y. Then here, I do that y times x, but the order doesn't matter when we multiply, so I'm going to write it as plus xy. All right. And then I have a minus a y squared. If you notice here, this minus xy and that plus xy, they cancel. And so I'm going to be left with x squared minus y squared. All right, this happened when we did variables, so it's definitely going to happen when we do numbers, because when we have numbers, variables represent numbers. So each and every time I see conjugates and I have to multiply them, I don't have to necessarily go through this FOIL method. All I really have to do is square the first thing minus squaring the second thing. And that's what I'm going to do from now on when I see conjugates. I'm not going to worry about foiling it out. Let's look at an example. This example, I have the square root of 10 minus the square root of 6 times the square root of 10 plus the square root of 6. Now, these are conjugates, and I'm multiplying these conjugates. Note, I want to make a special note here. When I multiply, notice I have the plus first and the minus second. The same thing is going to happen if I have x minus y times x plus y. All right, because with multiplication, the order doesn't matter. And I'll just go ahead and show you, right? When I FOIL it out, I'm going to get x squared plus xy, right, when I do this here. Now this minus y times x, remember the order doesn't matter, so I'm going to write it as minus xy, and then minus y times y is minus y squared. Notice these two things still cancel, and we're still left with x squared minus y squared. So it doesn't matter if the subtraction comes first or the plus comes first. As long as they're conjugates, we're going to have this kind of formula or this situation happen. All right, so if I look at this example here, since I have conjugates, what I'm immediately going to do is say, okay, well, I'm going to take the first thing that I have in my first slots, and I'm going to square them. And then I'm going to subtract from that my second thing squared. Okay, that's that x squared minus y squared, x squared minus y squared. And now that I have that, when I square a square root, all right, that's going to be the square root. Let's just write it out this time. That's the square root of 10 times the square root of 10 minus the square root of 6 times the square root of 6. Well, the square root of 10 times the square root of 10 is square root of 100, and 6 times 6 is 36, using that property for multiplication when the index is the same. Well, the square root of 100 is 10, the square root of 36 is 6, so I'm ending up with 4. All right, so this is another property here. When you square a square root, you're going to be left with just your radicand. I'm left with the 10 here. When I square this square root, I'm left with what is my radicand. All right, this is always going to happen, and it'll happen if you cube a cube root as well, right? So when we raise something to a power, it kind of cancels out the radical. All right, so we're going to keep that in mind as we continue to do that. Let's go to division. This is it with multiplication, but here my answer is 4. All right, let's go to division. All right, in these examples below, you see some division here, like 5 divided by square root of 20, square root of 27 over 11. We have radicals with the operation of division. We don't really divide by radicals. It's kind of hard to think of the concept of dividing by a radical because they're not perfect all the time. And so instead of dividing by radicals, we do what we call rationalize the denominator. Okay? Right now, all right, a rational number is a number that can be written as a fraction. And when we say rationalize the denominator, we mean make the denominator not but a rational number. And to be more specifically, we're actually going to make our denominators an integer. Okay? Or an algebraic expression that has an integer in it. All right? Right now, our number system has a bunch of stuff, right? We have whole numbers, we have integers, we have natural numbers, we have rational numbers. Well, when we have these radicals that aren't simplified completely, they're actually irrational. For instance, I'm going to scroll back up here. When I look at these numbers here, the numbers like 216 times the square root of 2, 112 times the square root of 5. These numbers are what we call irrational numbers. These two are irrational numbers. All right, so since a rational number is a number that can be written as a fraction, an irrational number is a number that cannot be written as a fraction. It's not a repeating decimal. It's not a terminating decimal. It's a number that has a decimal that does not repeat, goes on infinitely, and we cannot write it as a fraction. Now, we can do an approximation as a fraction, but we cannot write it as a fraction. All right, and so it's hard to divide by these numbers because they're non-repeating decimals. All right, and so instead of dividing, we're going to actually rationalize the denominator or make their denominators look like a regular old fraction because it's easier to divide by integers and stuff like that. Well, in order to do that, we've got to get rid of the radical that's in the denominator. And there's going to be two cases. The first case is when we have one term in the denominator. All right. When we have one term in the denominator, we're going to multiply our numerator and denominator by the radical that's in the denominator. We're going to multiply the numerator and the denominator by the radical that's in the denominator. And that's going to help us get rid of that radical. And notice we're only going to be doing this for square roots. Only for square roots. There's other methods for other types of radicals. We're only going to do it for square roots. Let's look at these examples here. Here I have 5 over the square root of 20. Well, I'm going to multiply the numerator and the denominator by the square root of 20. Notice I'm multiplying the top and the bottom so that I'm multiplying by 1, right? Square root of 20 divided by square root of 20 is just 1. So we're multiplying by 1, so it's the same thing. And notice I'm not going to cancel anything. What I'm going to do is I'm just going to multiply across. I'm going to have 5 times the square root of 20 all over. Well, square root of 20 times the square root of 20 is the same thing as square root of 20 squared. And we said that when we square a square root, we're left with just the radicand. All right, so I get 5 square roots of 20 over 20. Now, for me to simplify this, I'm going to start by simplifying my radical. All right, notice 20 is a rational number. So we've already rationalized the denominator. Now all we have to do is simplify. All right. Now 20 can be simplified. Square root of 20 can be simplified. 4 is the largest perfect square that goes into 20. It goes into 25 times. So I can rewrite the square root of 20 as the square root of 4 times 5. And of course, 4 is a perfect square. So if I take the square root of 4, I'm going to get 2. So that's going to be 5 times 2 square roots of 5 over 20. Well, 5 times 2 is 10. So I get 10 square roots of 5 over 20. Now, if I think about this, my radical is simplified, but my numbers that are not in my radical are not simplified. For instance, 10 and 20 have a common factor of 10. So if I cancel out by 10, or divide out by 10, 10 goes into 10 one time, it goes into 20 two times. So I get 1 times the square root of 5, which is the square root of 5, all over 2. And this is my most simplified answer, all right? So we made our denominator a rational number. where we had one term by multiplying the numerator and the denominator by the radical that's in my denominator. Let's look at part B. In part B, we have the square root of 27 over the square root of 11. Now, it's a little bit different in this case. What I'm going to do is I'm going to rewrite this as the square root of 27 over the square root of 11. All right, now it's a little easier to see that when we multiply the numerator and denominator, we're going to actually multiply it by the square root of 11 over the square root of 11. Okay, and now I'm going to multiply across. Well, square root, we both have square roots, so 27 times 11 is 297. And when I multiply the square root of 11 times the square root of 11, we get the square root of 121, which is still 11. And so now we have a rational number here. This is our rational number. And now all we need to do is simplify. Well, if I think about my list of perfect squares, the largest perfect square that goes evenly into 297 is 9. 9 times 33 is 297. And I can take the square root of 9, that's 3. So I get 3 square roots of 33 all over 11. Now, what I don't want you to do in this type of example is try to cancel out this 33 and the 11. The 33 is under a square root, the 11 is not, so we cannot cancel. We can only cancel the things that are outside of the radical with the things that are outside of the radical. So in this example, we're completely simplified. Let's look at one more of these types of examples. And this is an example where we have a variable in there. Okay? Just because a variable is in there, it doesn't mean we're going to do anything different. We're actually going to do the exact same thing. So I'm going to multiply my numerator and denominator by the square root of 18a. Okay, my numerator is going to become 8 times the square root of 18a all over 18a. All right, this is rationalized. I have a variable with it, but it's still rationalized. And so when I do this, I'm going to simplify the square root of 18a, right? The largest perfect square that goes evenly into 18 is 9. So this is going to be the square root of 9 times 2a over 18a. Of course, the square root of 9 is 3, so I get 8 times 3. And I have my square root of 2a still under my radical, all over 18a. Well, 8 times 3 is 24. So you get 24 square roots of 2a all over 18a. And of course, 18 and 24 have a common factor of 6. 6 goes into 24 4 times. It goes into 18 3 times. So I get 4 square roots of 2a all over 3a. And that is going to be my final answer. Okay, don't try to cancel out these a's because one of them is under the square roots, under the square root. And so this is my final answer here. All right, that's the method that we use when we have two numbers or one term in our denominator. Now we do something a little different when we have two terms in our denominator. Okay, instead of multiplying by the radical that's in our denominator, we have two terms. All right. What we're going to do is actually multiply by the conjugate of the denominator. All right, because when I multiply my conjugates, I'm actually going to be squaring my two terms, right? I had that formula earlier that I say I square my first term and then square my second term in the binomial when we have two terms, when we multiply conjugates. And so we're going to do that, and that helps us rationalize our denominator when we have two terms in the denominator. Let's look at this example. 4 square root of 2 minus the square root of 3 all over 2 square root of 2 minus 3 square root of 3. The rational expression that's in my denominator, or the radical expression that's in my denominator, is 2 square root of 2 minus 3 square root of 3. I'm going to multiply by the conjugate of that, which will be 2 square root of 2 plus 3 square roots of 3. And of course, we got to multiply the top and the bottom by that thing. When we do that, it kind of sets up a forward method. So these types of examples can get very complicated. Okay? So I'm going to multiply using my FOIL method on my numerator. And I'm going to write it all out so I won't mess up. So 4 square root of 2 times 2 square root of 2 plus 4 square root of 2 times 3 square root of 3, all right, minus the square root of 3 times 2 square root of 2 minus the square root of 3 times 3 square root of 3. And I'm going to divide all of that by, okay, those are conjugates in my denominator, so I'm going to have 2 square root of 2 squared, those are in my first lots, minus 3 square root of 3 squared. There we go. All right, to simplify, I get 4 times 2 is 8, square root of 2 times square root of 2 is square root of 4. 4 times 3 is 12, square root of 2 times square root of 3 is the square root of 6. 2 is my only thing on the outside, so I get minus 2. Square root of 3 times the square root of 2 is 6. And minus a 3 times the square root of 9. My denominator, when I distribute this 2, right? Since that's multiplication, I can kind of like think of my distributive property a little bit, right? So I have to square the 2, which will give me 4. And when I square root the square root of 2, I get 2. So that's 4 times 2. Likewise, when I square this 3 here, I get 9. When I square the square root of 3, I get 3. And now the rest is simplifying. Okay? Square root of 4 is 2. I'm sorry about this. I'm not sure why this is happening. It'll be 8 times 2. Square root of 12 and the square root of 6, they are like terms, so I can combine them. That's plus 10 square roots of 6. And the square root of 9 is 3, so I get minus 3 times 3. All over, well, 4 times 2 is 8. 9 times 3 is 27. Okay, so we're almost there, right? 8 times 2 is 16. So I get 16 plus 10 square roots of 6 minus 9 all over a negative 19. Okay, 16 minus 9 is 7. So I get 7 plus 10 square roots of 6 all over negative 19. And if you wanted to bring the negative on the outside, that is perfectly fine. So I get 7 plus 10 square roots of 6 all over 19. And my plus sign is trying to disappear. And this will be my most simplified answer. This is how we want to leave our answer. All right, and this concludes our video on multiplying and dividing radicals.